This is a very important postulate that we're going to be constantly using throughout the school year. The segment addition postulate. So imagine, if you will, that we have a line segment made up of 3 collinear points. It doesn't matter where the B is, as long as we have these 3 points in this line segment. Note that we have the length from here to here is AB. From here to here is BC. And the entire length of this line segment is AC. We propose to you that if we were to add AB to the length of BC, it would be the entire line segment AC. Then let's consider a trip through Georgia. We'll start off here in Albany with a B, and we're going to go ahead and get some food and gas at Macon. So that distance can be represented by the line segment BM. We then leave Macon and end up in Athens. That smaller line segment can be represented by MA. The question is, what was the whole trip? It was from Albany all the way to Athens. So that's BA. So what we're doing is we're using the segment addition postulate to represent a long trip that we break up into smaller trips. Okay? The trip from Albany to Macon, and then from Macon to Athens, is the entirety of the trip. If we go backwards now, so if we start at Athens and then make it back all the way to Albany, if we start at Athens, stop at Macon, we can represent that distance by this line segment AM. And then after a small stop at Macon, we go ahead and leave Macon and proceed to Albany, and we're home. That entire trip from Athens to Albany can be expressed as AB. Notice how this is the same trip forward and backward. Notice the order of the letters. Okay. For example, here was MA, here it's AM. But if we consider, for example, if we start at Macon and go to Athens, that's an 80-mile trip. Or if we consider A to M, start at Athens, go to Macon, it's still an 80-mile trip. So even though in this case the letters may seem switched around, it still represents the same distance. Whether you walk forward 5 steps, or you walk backward 5 steps, or you walk to the side 5 steps, it still is 5 steps. We note that the total distance for the entire trip is going to be 170 miles. It doesn't matter if we start in Albany and finish at Athens, or if we begin at Athens and finish at Albany. It's still 170 miles no matter what. Okay? So whether we go forward or backward, it doesn't matter. Right? Now, some of you may be thinking, well, Mr. What about negatives? This is geometry. This isn't necessarily algebra where we have the number line and we have to worry about negatives. So in geometry, in physics, in sciences, we generally tend to think of what's called the absolute value. The absolute value is a very practical thing that we do in real life because we don't consider that you go negative 170 miles when you come back home. The odometer in your car reads that you traveled 170 miles. Let's now look at problem 2, where we have a pretty extended piece of line with some segments in between. So you'll know that there's a PQ segment here, a QR segment here, and an RS segment here, and that the entirety of this line segment is represented by PS. You'll know that there's arrows, meaning that this is a line that goes on forever. You see that points P, Q, R, and S are all collinear. Now at this point, if you haven't noted, geometry is a very vocabulary heavy subject. So you might want to keep track of all these vocabulary words somewhere, and definitely have all of your notes available with you at all times because stuff's going to come up over and over again. So what kind of relationships could we write based on this diagram here? Well, we could say, for example, that PQ plus QR, that is PR. Or we can say QR plus RS is from here to here, QS. Are you noticing that there seems to be like a bit of a pattern here? Notice how we end this one with Q, we begin with Q, we end this one with R, we begin with R. The segment addition postulate tends to generally do that. There's going to be a connecting point. Now, whether we see it algebraically or not, geometrically, line segment QR, there's just R in between the two of them, and that's the connecting point between them. Okay. We can also express a super one. So we do PQ, and then QR, and then RS. This would be the entire trip. For part B, let's go ahead and use this large segment addition postulate that we set up for this diagram. And this time they're going to give us some values. So for example, PQ is going to be 3. So this is going to be 3. RS is going to be 2.5. And PS is going to be 14.3. And I'm going to go ahead and bring everything else down to equal. There was a plus here, a QR, and another plus. And we're going to go ahead and solve for QR. So we are doing a little bit of algebra, just very little bit. Actually, this is more like pre-algebra at this point. And we're going to go ahead and combine this 3 goes with this 2.5. And then I want to go ahead and get the QR by itself, so I'm going to subtract 5.5 from both sides. And I get QR equals 8.8. So if PQ were 3 and RS is 2.5, and this whole entire thing was 14.3, then QR would have to be 8.8. So I can leave that to you to confirm and to double check, but if you were to add this number to this number to this number, you should get 14.3. One last quick note that I want to bring up is this idea of the connecting point. So just because you have a bunch of letters and segments doesn't mean you can just add whatever you want and get lucky. We can't say, for example, that PQ plus RS is PS, because we're only looking at this length and this length, and there's no connecting point in between them. So we're pretty much we're going from P to Q, and all of a sudden we're jumping all the way to RS. And the segment addition postulate doesn't work like that. I must have a geometric connecting point that joins them. So in our giant long one, for example, we go from P to Q, then we go from Q to R, then we go from R to S, and that gives us this relationship. For your summary, I want you to consider, is AB plus BC equal to AC the same as BA plus CB is equal to CA? Here's a drawing in case if it helps you out. Think about it. Comment.